What entanglement actually means? Quantum information theory is an application of quantum mechanics that studies the processing of information by quantum systems. Such information are expressed in terms of quantum bits or qubits that can exist in superposition of states. And the qubits can be entangled, which means that a state of one qubit is dependent on the states of the others. And this entanglement can be used to perform computations that's impossible to have on classical computers. And the Bloch sphere is a useful tool to represent visually the state of the qubit and understand the effects of the quantum operations that we perform on this qubit. But then the question becomes how we understand the entanglement from all of this. There are three aspects in which we can understand entanglement. We can understand it intuitively, but also mathematically and physically. Let's assume a universe of which I have two versions of myself, me and my identical twin. Now, both of us will carry a sign with a binary number, either 0 or 1. In this situation, we have four possible configurations or situations in which we can carry those signs. The first one, I can carry the 0 sign and my twin carries the 0 sign as well. I can carry the 0 sign and my twin carries the other sign, the 1 sign. And vice versa, I can carry the 1 sign and my twin carries the 0 sign, or both of us carry 1 sign. These are the possible four configurations in which we can carry information about the 0 or 1. If you find me with a 0 sign, my twin is still in the superposition. He can have 0 or 1. So there's two configurations for my twin. In other words, my state is not coupled or dependent on his state, and vice versa. His state is not dependent on mine. Let's assume we have eliminated two configurations and now we ended up with two configurations or situations where we both carry the 0, 0 or the 1, 1. Hence, we see the entanglement now. If you find me carry the 0 sign, it means that my twin carries the 0 sign as well. And vice versa. If he carries a 0 sign, I'm carrying the 0 sign as well. Similarly, for the situation of 1, 1. If I'm carrying the sign of 1, he's also carrying the sign of 1. And this means we are entangled. But to get a deep understanding of entanglement, let's look what happens on a quantum level. So quantum systems can be in a superposition of states. A quantum system can be expressed as a linear combination of several states. Every state represents one situation or one configuration. Here we see a quantum system that's expressed as a linear combination of state 1, state 2, state 3, and so on. And they have some weighting factors. Those weighting factors represent the probability of finding this quantum system in this particular configuration or state. To describe superposition or this linear combination, we use what we call a wave function. Wave functions are a mathematical representation of the state of a quantum system. In fact, the wave function is a complex valued function that describes the state of a quantum system. It contains all information about this particular system that can be known. It's also an abstract mathematical object that contains this information. And to comprehend wave functions, we sometimes need to project it either in space, time, or sometimes the momentum. Now suppose we have a quantum computer of two qubits only, qubit A and the qubit B. The first qubit A can be in a superposition of 0 and 1. Similarly, we can have a wave function that describes the qubit B in a linear combination or a superposition of 0 and 1 with different coefficients, gamma and delta. As we can see here in our 2-qubit quantum computer, we can describe every qubit by a separate wave function. So we have a wave function describes the first qubit A as a linear combination or a superposition of zeros and ones and with alpha and beta. Similarly, we have another wave function, psi B, which describes the linear combination of 0 and 1 by gamma and delta. If we combine these two qubits, we get a superposition of all possible states of the system, which are in total 4. We can have a configuration where both qubits are 0, 0, or the first or A is 0 and B is 1, or A is 1 and B is 0, or both of them are 1s. Then we can describe the superposition of the states of this 2-qubit quantum computer by the following wave function. We have a combined psi of AB that's equal to A00 plus B01 plus C10 plus D11. This means that we have 4 configurations, and every configuration has a weighting factor, which is A or B or C or D. That represents the probability of finding these particular 2 qubits in a situation or a configuration in which either they are in 00, 01, 10, 11. And of course, A, B, C, and D are complex numbers that satisfy the normalization condition, which means that if you square the complex conjugate times the factor itself and you sum all of them in this way, you should get 1. Now let's measure the qubit A. Typically, a quantum system of 2 qubits is described by the following that we have seen before: A00 plus B01 plus C10 plus D11. If we measure the qubit A, we can have one of the following states. We can find it either in 0 state or 1 state. Now suppose we measure the qubit A and we get 0 only. The system will collapse and the new state of the system will be state phi equals E times state phi equals E times state of 00 plus F01. If we zoom in, it means that the first qubit now we find it really in 0 because it is represented by the first digit. In this situation, if the first qubit A is 0, still the qubit B can be in 0 or 1, as we see here. In that sense, the qubit B is still in a superposition. Its state is decoupled or independent of knowing or the measurement that happens to state A. Now, let's back to the way that we wrote the state psi. So it equals A00 plus B01 plus C10 plus D11. Now suppose we have performed an operation that eliminates 2 configurations out of those 4. So we will eliminate the states 01 and 10. Hence, the new state of the system will be state phi equal A00 plus D11. And of course, these are not normalized, so we have to renormalize them, and this is the way to go in renormalization. Hence, the new state will be state phi equal alpha 00 plus beta 11. In this situation, we can see that the qubits are entangled. Knowing the state of the first qubit will allow us to determine the state of the second qubit. In that sense, if the first qubit is 0, the second one will be 0. And if the first qubit A is 1, then the second one will be 1. And here we see clear dependence between both. We have 2 possible situations for the physical system of the 2 qubits. And if we know the state of the first one, knowing the 2 situations, we can determine the state of the second one for free. And this is what we mean by entangled states, or the 2 qubits are entangled. By knowing the first qubit, we can know the second one for free. Mathematically, that means we cannot defactorize them or retrieve them back. We cannot retrieve the original states of the qubits out of the box from the combined state. And here we see clearly the entanglement. We have 3 aspects for entanglement. Intuitively, it means that in this 2 system of 2 qubits, if we know the state of the first one, we know the second one for free, because we have only 2 situations or 2 configurations in which that either both of them are in 0 state or both of them are in 1 state. Mathematically, that means we cannot defactorize or retrieve their original states back. And physically, it means that the measurements of the states of the qubits are dependent of one another. So if we measure the first one and find it in 0, the second one will collapse and will be in state 0 as well. And this holds also for the second situation. If we measure the first qubit to find it in state 1, the second qubit will collapse and will be in state 1 as well. And this is what we mean by quantum entanglement.